All right, we got guesses? I am ready. Hannah, you're always the first one. Always ready to go.
160.
160. All right, Britain.
132.
That's a good answer. I'm going to say 133.
118.
Ooh.
No.
Say 127.
Ooh, that's a good guess.
All right. 3.
94.
Going low.
All right, Nancy.
133.
All right, Ashley.
156.
Jillian.
182.
Did I tell you a kid in my other class cheated on me?
How?
You can look up the website and you can like see the day.
Yeah, that's so
They wanted the clout.
I was so mad. I was like, you ruined that.
98. How'd you figure out he cheated?
Because it was one of the ones with the miles where the answer is like over 2,000 miles and he guessed it right on the first time. I'm like, oh no. With a smirk.
106.
Over 2,000 miles.
All right. Elena. I've had people in previous years look them up every single time.
That's so annoying.
I would
That takes the fun out. Yeah, I would get so upset.
137.
Ooh.
Michaela? Wow, my handwriting is really taking 99 down. What? No one likes my.
Oh, I like how it's like around the edges of like.
136.
Okay.
110.
Okay. 150. Anyone else? Probably everyone. All right. Are you ready for the video reveal? My AB class did not enjoy this.
Yes.
Oh, he's gonna scam us again.
Does he put them on individually?
Oh, what is that?
It goes faster, don't worry.
Oh, dang.
Hey, I knew it.
Oh, wait.
Hey,
Oh.
Oh, 150. I said 156. I said 150. No.
Always try. He's so willing.
What? Scam.
Oh.
One more.
Oh.
Oh, it fell back out.
You got it though. You got it. You can fit more.
Did you get it exactly?
I got it exactly.
Is Ashley a cheater?
I did not. I saw what you know one.
What was that?
Oh, where are you?
Exactly right today. Way to go. All right. So, okay. I'll get one. I've been handing out so many stickers over the past couple of classes because apparently that's the only way you guys will do your problem sets. So,
I love stickers.
honestly, I should have thought of that a while ago. So, I'm gonna come around with new notes for today. I will say these notes are a little intense, but if we go step by step, it's not too bad. I would also love your problem set question is a little bit different than some. Whoa, okay. Let me take that off. Sorry.
Do we have problem set time today?
Yeah, so we're gonna try to at least there's 2 questions about Lagrange. I would love to get one of those done in the problem set because I forgot to kind of change the problem set question to mirror the notes a little bit better. It does mirror it if you're like thinking very conceptually, but I kind of want to help you set it up a little bit. So I definitely want to get one of the Lagrange questions done. The other one actually has to do with a different error, which we'll talk about today. You'll notice that when I pass out the notes, we're going to be kind of philosophizing up here for the first page or so. So there's a lot of kind of lingo and stuff that we're going to discuss. So we're not going to do too much actual calculation until we get to the second page. Really, we're focused on what is that? Nina. Yeah. No, but there's just a lot of like there's stuff we have to talk about before we actually do that. Because it's kind of a theorem, actually, the Lagrange error bound. It's part of something called Taylor's theorem, and we're going to kind of hand wave part of it and actually do other parts of it. So I'm going to talk a lot. So that's kind of what you signed up for, right? Listening to me talk a lot. Yeah. I haven't held my breakfast in forever. Yeah.
And this is
So I'm gonna try to bribe you to get
Can't we miss it?
So if you get here really early, I'll get you bagels. And then there's like, I'm 4, so.
Yes, please.
Can't get that many bagels. Yeah.
Hey, too.
It's like at the top of the materials page. I did email it to you guys as well, or you can use the QR code.
Well, we can find out that.
I only got him.
Let's go on here. It's not super time sensitive. Right?
This is the pencil you gave me, like.
And you've cherished it for this long.
No, yes, it happened.
Nazi, I knew you cared about me.
It happened yesterday. It was just that.
All right, I need my notes for this.
I remember you. Yeah,
Hopefully, okay. At least I'm gonna try to get like the Lagrange.
Oh, maybe. Yeah. I was like zoning out. I was
Where did this go? Ella's mom made it. I'm trying to make sure.
It was a joke.
All right, are we ready?
Yeah.
So, going along with the kind of theme of this unit, I hope one of the themes of this unit that you've kind of seen is that Taylor series in general, none of the particular math is super challenging. Some of it's challenging, not terrible, but it looks terrible. That's a lot of the same stuff that's going to go on with Lagrange today. None of the particular choices we're going to be making are horrific, but it's going to look bad. So we just have to be willing to write, willing to take choices one by one, and kind of willing to think through each step. So what we're trying to do today is we're going back to the idea of Taylor polynomials. We've been doing Taylor series where our series goes on forever and it's actually equal to a function. We're going to go back, though, to the land of approximating. So I'm using like 6 terms to approximate something, 4 terms to approximate something. So I'm not going on forever. So we're going to be talking about partial sums. The first few terms of our series, we're going to plug in, we're going to find a number. It's going to be kind of close. I won't use this word a ton today, but the tail would be called the rest of the terms. So like if I added up the first 5 terms for my 5th partial sum, 6 to forever is the tail. What we're going to be finding today and talking about today are a couple of things. One, we'll be talking about the remainder, which we also use the word error. For the sake of argument, these, remember, are the same thing. They just give off kind of different vibes. Remainder kind of gives off the vibe of like, hey, these are all the terms that remain, add them up. Error kind of gives us the idea of like how far is our partial sum off, but our partial sum is off by how many terms remain. So same thing, interchangeable words. We're actually not going to be finding those today because I would need a calculator. I would need to be able to find the actual sum of that series. What we're going to be finding today is what's called an error bound. When I say bound, I mean something that's definitely bigger than the error. And we're going to try to find it today in a way that's relatively easy to find. So a lot of the choices we're going to be making are ways to make that error bound easier to find than if I had to like grab a calculator and do some huge calculations. All right. You guys just took the Unit 8 test. We talked about an error bound in there. It was for alternating series. I want you to look at your neighbor, hope that they remember, or maybe you remember, how did we find alternating series error bound? Ponder, think. All right, is anyone brave enough to tell me what my error bound was? Those windows don't open, so the fact that those blinds are moving is not good.
It's like the term after the
A ghost. Is it raining? It feels really warm in here, doesn't it?
It's like musty. It's like muggy. It's like muggy.
Every day.
It's been there all year.
It's
It's
just,
our
I can
lesson
feel like a
notes.
breeze.
That's great because that window doesn't open. Cool. All right. Does anyone remember alternating series error bound? If you had to describe it, if I add up the first 6 terms, what's the bound for the error? The term after it. It's like the next term up or the first truncated term. So I'm going to call it the next term up. We will revisit this again today because this is going to be easier than Lagrange. So if we notice our series is alternating, we'll be able to use that. Just to review some notation, we're going to use both of these today. We had our R sub n, that was more of our remainder notation. Or we could write it as the actual sum minus our partial sum. Now, those are the actual remainder or the actual error, and we claimed that those were less than or equal to a sub n plus 1. So if you notice that I plugged in 6 for the number of terms for n, then we'd be looking at a sub 7. If I plugged in 100 for the number of terms for n, I'd be looking at the 101st term. So what Taylor's theorem, that is Brooke Taylor, the creator of Taylor series, what that says is essentially our error. There is a perfect place where I can plug in a derivative, my n plus 1th derivative, and I can actually find something that's equivalent to the sum of the rest of the terms. And that looks like our next term up. So you're seeing all of those n plus 1s. But that perfect value that I could plug in and actually find the error is this value z. We are never, ever going to find z, but I want to kind of talk about what z is. It is what I could plug in to that n plus 1 derivative. So this actually equals, if I stop at 6 terms, this equals the sum of the 7th through infinity. Now, we won't actually know what z is because we don't have that much power in our mathematical skill. What we're going to try to find is a number that will get us something that's definitely bigger than that n plus 1th term over the interval between our center and where we're approximating. And we're going to spend the majority of our day today trying to figure out how to get the bound for that specific piece of this puzzle. So when we talk about the remainder, this part is talking about our actual remainder, and we're going to be talking about our remainder bound or our error bound. Since that's the... All right, so the most important part of what you need to be writing down is I want to take a look at this formula here. This is going to be the one we're really using today. And I want to label all the letters because there are a heck ton of letters in this. All right, what do you think R stands for? Remainder. We were just talking about it. And what word might I use interchangeably with remainder? Error. All right. Now, X. That's usually the X value that I'm plugging in. So if you think of on your problem set, there was one that asked you to approximate E of 0.2. That 0.2 was where you were approximating. So this X value is going to be where we're approximating. Whatever X value we are plugging in to make that approximation. You guys sound focused today. Cool. Good vibe. All right. I'm also tired. Thoughts on C? Center. Thoughts on N? So normally this has been, think of like the N here is the biggest power on this. What did I call that biggest power? Word that starts with the letter D. Degree. So this is going to be the degree of our partial sum. Ooh, that's not how you write it. And again, our main focus today is going to be on this bad boy. There's two things we're going to focus on when we're finding it, and they might not make a whole lot of sense now, but we're going to talk through this a whole heck of a lot. So there are two conditions we're really working with. Something easy to find. So we're going to err on the side of being easier rather than harder, and definitely bigger. Again, that will make more sense as we start to practice. You're going to notice that as we do these questions, I'm going to kind of do them in two steps. One where I kind of write out this remainder formula in its entirety, making all of the substitutions except the max part. And then I am going to work on that maximum choice. So I'm definitely going to have two steps to this process. All right, you ready for the first Lagrange? Yes, you are. It's going to be fine. It's actually not that bad. All right. So usually to do Lagrange, we want to actually make an approximation first because we're finding error for an approximation. Might as well actually make that approximation. So let's review how to write a Taylor polynomial. I am going to read this question in the near and tell me anything that's important. So we're writing the third degree Taylor polynomial for f about x equals 2. What did we just learn? All right, so we're going up to what power? Cubed. Yep. What does about x equals 2 mean? Center's 2. All right. We're going to use it to approximate f of 2.3, but let's write that guy first. So I'm going to call it p sub 3. That's a polynomial of degree 3. You could also call it p of x or t sub 3. Any fun thing. What's the first term? Great first term. Thoughts on the second term? Don't just stop by saying 4. Cool. Next one. X minus 2. Yeah, you could if you wanted to. Make sure that's squared. Then my last term. Look at all those different types of 2's I made. Wow. All right. What do you think it means approximate f of 2.3? All right, we're going to plug in x is equal to 2.3 to our Taylor polynomial. If you don't already have one, you're going to need a calculator today. If you need to borrow one of mine, they're behind Matt and Emery. I want you guys to plug in, and let's see if we can all get the same number. I'm going to take attendance while you guys plug in. Yeah, why is it so awkwardly like warm and muggy in this room today?
Because that's how it is outside.
Oh, that's fair. But did they switch over to the? Oh, do you guys practice in the morning?
Yeah. Oh no, someone spelled it out.
Yeah, it's fine. The masking tape I was using didn't work that well. It wasn't Jillian, right? Good. Like, yeah. No, so we're now approximating again with a specific number of terms, so you're correct. There's no plus dot. Alpha y equals, enter. Yeah. All right, who did we say wasn't here? Alanowski. Gribben was late. Should I mark him tardy?
Yes.
Yes. I'll mark you tardy.
But I was doing this.
You were still late to my class. Nothing's going to happen. I can tell you that right now. They are dealing with way bigger issues in the main office than Nate Gribben being tardy to one class. Seeing as they had to move the in-school room to a different room because there's too many people in school. I think there's like 10. I don't know. I had to go fetch, because you can, as a teacher, I can go pull you to come to my class. I had to go get 2 people for my third block.
I know. No, I know. There's so many ways to like have them in class.
Yeah.
I remember one of my teachers was like, "Nah, just leave them."
No. What do they do?
Like,
You sit there all day.
no. You do to get it. What's
Like,
that?
I think it's a lot of vapes currently.
Oh yeah. There's like a bunch of freshmen in it right now.
I know. All right, did anyone get a number? Something slightly south of 7?
Yeah, I got 7.029.
All right, you might want to plug in again. All right. So, cool. We get a number. Great. We want to know, how close is this number? I want to get an upper bound, meaning a number that's definitely bigger than how far off I am. I want to get to know how close I'm getting. Because that didn't feel like too much math to do to get an approximation. So maybe I'm real far off. Who knows? So we're going to go from easiest to hardest on kind of how Lagrange works. But what I'm going to start with every time is essentially plugging into the formula. Since this is our first question, I'm just going to copy down the formula from the front page. Eventually, we're going to have this memorized, but I would like you to know it doesn't look that scary because it's really got the same vibe as that next term up kind of thing. So I've got my next derivative up. I would, because I am, but yeah. All right, we're gonna have x minus center to the n plus 1 all over n plus 1 factorial. So it looks just like the Taylor series formula, except everything's got an n plus 1 in it instead of an n, and we've got that weird z there. No. How would I pronounce this? Yeah, you could make one. If you come up with a good one, let me know. You'll probably have it relatively memorized by the end of today. All right, so let's actually apply this to this problem. What would n be for this problem? It's our 3. It's a 3rd degree. So what I'm going to do is I'm going to try, actually, I'm going to write something else here. What x value did we plug in? Super sure.
I can feel a draft from here.
I mean, it might be like unintentionally open. Like this. I want to say, like, the window does not open. No window. We're one of 2 classrooms in the entire school that, like, the windows literally don't open.
That's really dangerous.
It is really dangerous. We've tried to get safety and security to help us with it, so they refused. So I don't know. No, it was like not the safety and security people here. They did a great job with advocating for us. The people at the admin building did not. All right. All right. So what I'm going to do first, let's focus because this is important. The first thing I'm going to do is I'm going to replace everything but the z, essentially. So what are all of these n plus 1s now going to be? 3 plus 1, 4. All right, so I've got the 4th derivative at this perfect value z. Now notice when that z is in there, there's actually an equal sign here. So we're setting up something that's actually equivalent to the remainder, exactly how far off this guess is. What x value was the one we plugged in to make our approximation? 2.3. What was our center? What will this power be? What will the factorial be? 4. So notice, just like when we were making the Taylor series, the number derivative, the power, and the factorial all match. So kind of in terms of memory, at least those all match right there. All right, now you're going to notice I'm going to change from this equal sign to a less than or equal. Because what I'm going to do is I'm going to replace all of this blue thing with a number I know is definitely bigger than this derivative on the interval between where I approximated 2.3 and where my center is 2. Let's go back to the question and see if we can find a convenient number. The fourth derivative of f satisfies, and I apologize for my typo, the inequality. My second block wanted to keep the t for fun. The inequality. The fourth derivative is less than or equal to 9 for all the x between my center 2.2 and my place I'm approximating 2.3. So first option for finding the max, they literally just tell you. So they have told me that 9 is definitely bigger than the fourth derivative on the interval I care about, between 2 and 2.3. So what I'm going to do, as I equals with the less than or equal to, I'm going to replace my fourth derivative with something I know is definitely bigger, 9. I'm going to simplify a little bit. Now, some people in my second block were like, well, why wouldn't you try to see if it was like smaller than 8 or like smaller than 7? Because they told me it's 9. That's easy to find. They just told me I don't want to think more than that. I'm trying to find an error bound. I'm just trying to get a number that's definitely bigger. 2.3 minus 2. Yep, just simplifying a little bit because I'm about to plug into my calculator. I would love to know this error to 3 decimal places. So if you could plug in. Personally, I don't like plugging in factorial. So when I plugged into the calculator, I did 9 times 0.3 to the 4th over 24. Because I actually don't know where the factorial button is. There is, it's in math somewhere. See, that's too much work. Also too much work.
I didn't tell you. That thing stuff, like, has to be written on the board, and she said it was like about China. There was like an exclamation point at the end, and I was like, why should we factorial just go? Because I'm so like brainwashed.
No. Calendar invite for June 3rd. I see math everywhere. Oh no. All right. Did anyone get a number? Oh no. All right. Wait, hold on. Though. Do you guys get 0.003? Cool. Apologies for taking a second. All right. You know, sig figs are stupid.
Do those zeros in the front count? No, they don't. Zeros in the front don't count. Maybe 4? 0, 0, 3, 0, 7, 5. You round it. You round it. Oh, calculator.
All right, we're back in it to win it. So, 0.003. I would argue, for the amount of math we did, that gets us pretty darn close. Not gonna lie, that was not too hard to do, and I'm okay with that. We're almost at like AP test accuracy here. Now let's see if we could find an interval where we know f of 2.3 is. Does anyone remember how we did the interval for the test? All right, we could plus and minus our error from our partial sum. So we could do 6.921 minus our error bound and 6.921 plus our error bound. So let's see if I can add and subtract. 6.918. 6.924. So could we get 6.922? Would that be okay? Yeah. 927? No. I would argue that's a pretty darn good error for the amount of math that we did. So what we're going to investigate for the rest of class is how can I make that kind of blue thing, that derivative, whatever derivative it may be, how can I make it more interesting to find the max of that? And the first way we're going to do that is we're actually going to look at my Lagrange question from my AP exam in 2008. So I'm setting the stage. It's 2008. I am 17. I am in the Augs gym. I have almost cried looking at one of the calculator questions. Don't worry about it. I made it through. Yes. I am 31 years old now. Good job, Abby. Wow. All right. I have done 45 multiple choice questions. I've done 5 free responses. I open up the very last AP calculus question I'll ever do, and I see this gosh darn table and some Taylor series stuff. And I'm like, all right, let's roll. How many?
Oh yeah, 5.
Got a 5. No, it's actually a good lesson because that calculator question that I really didn't do well on. I see the calculator questions. You can go back during the non-calc and like do them without your calculator. I figured it out like during the first response non-calc part and went back and furiously set up all my work. I think I even wrote them a note of like, sorry, I don't have my calculator anymore. I was the valedictorian. So our grading system was all different though. So like we didn't have minuses, so a 92 was a B plus. Did I not give off that vibe already? Yes. We got a 0.7 bump for AP instead of 1, and you didn't get a bump for honors classes. Wow. We took less APs though, so I took I think 8 overall. I thought it was good. Wade Byard has the video. I know that because no, I don't know if he was there, but they interviewed me when I came back to teach here, and they included a clip of that. Yeah. But look at this stupid table. I was so mad when I saw this thing on the AP test. 488/3 and 448/3 necessary? No, but irrelevant to the discussion here. I do really like this question though because it gives a really good way to find that max. So let's investigate. Let's figure it out. So we got a function h. We got derivatives of all orders, meaning I can take as many derivatives as I want. Cool beans. X is greater than 0. Sick. All right. We've got the first 4 derivatives in the table. If you get a table that has this much information in it, odds are you're probably not going to use all of it, and that's okay. They're going to give you extraneous information at parts. We've got H. These derivatives are all increasing. It does appear to be increasing. So if you look at kind of at each specific function and roll down the table, the numbers are getting bigger. It's just nice to get verification that that is true the entire time. So this, I believe, was the last part of this question. We're going to use the Lagrange error bound. So again, it's kind of nice, like some of the other topics we've done this year, they're going to kind of come out and tell you Lagrange error bound most of the time when they want you to use it. We're going to show that the 3rd degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with error less than 3 times 10 to the negative 4th. I also like using this question because it's the only time I've ever seen them use scientific notation. So just so we can make sure everyone's on the same page. So again, the first thing I'm going to do is I am going to set up that error bound, filling in everything except that kind of derivative at z. You can use alternate notation here. So just another way to write the error, I could say the difference between actual h of 1.9 and my polynomial approximation, which was 3rd degree at 1.9, this would be equivalent to saying like the remainder of the 3rd degree at 1.9. It doesn't really matter which way you do it. I would just try to reflect whatever notation they're using in their question. So just to give you alternatives. All right, so first thing we did was the derivative. What number is going to be up in that derivative now? Is it 3? Is it 4? Yeah, we got to do n plus 1. Our 3rd degree now is 3 plus 1 or 4. We're going to keep the z. Next thing was x minus c. The x was where we are approximating. What is that number? 1.9. All right. The c was our center. Where's that? 2. What word should we look for the center? About. So about x equals 2. What power is this going to be 2? 4 over 4 factorial. Now, I used 4 a lot today. I promise it's not always 4. It seems to be 4 in a lot of the AP test questions. I think it's because Taylor polynomials, like their sweet spot of being interesting but not tedious, is 3rd degree. So you're going to see that a lot. All right, so let's talk about now this guy right here. It's our big choice. First thing, I don't like that I wrote f. Does anyone else hate that I wrote f? Yeah, our function's named h, so I'm going to change that. Apologies that I didn't catch that earlier. Notice it when I was looking at the table. So first of all, I would argue that like most of this table is absolutely meaningless to this question. So I'm going to pull, if anyone knows James Dick, he did this last year on one of his quizzes. He crossed out everything that was irrelevant in the table. And I was like, love that for this question because there's so much information that's irrelevant. Well, that's why writing in pencil is great. It is, well, this is probably the last part of the question. So there you go. Michaela. Yeah, so we're just working with that 4th derivative. So I only care about this column right here. So you probably needed it earlier in the problem. But for right now, we're looking at this guy. All right, so I need to figure out, I'm going to say this a couple of times, and then I'm going to ask you to make a decision. We have 3 values for this 4th derivative, the one at 1, the one at 2, and the one at 3. I need to know which one of those 3 values I should use. Now, remember, we are trying to maximize the 4th derivative on the interval between where I'm approximating and my center. So again, maximizing the 4th derivative between where I'm approximating and my center. I want you to talk to your table and figure out, should I use the derivative at 1, derivative at 2, or derivative
I was in that reading it back in the day. Hold on. Who graded?
Yeah, and then whatever Bernie said, I'm like, holy cow.
I used to have a full table of people that were like, one was 6'5", one was 6'3". The shortest one, it was like 6'5", 6'4", 6'3", and then like 6 foot. And I would talk to them, and then they would get up to leave, and I'd be like, oh. All right. Any thoughts? Which one am I using? Should I use 18, 584/9, or that last one? You guys think the one at 2, 584/9? Why not this one? It's the biggest. All right. So if we're kind of looking between 1.9 and 2. So really, our two options are these two guys here. I would argue this is too far away. Now, this might be the case where that number does work and makes us less than this number. You could try it. It might be good. But I would think a better choice would be the one at 2, because it is kind of the maximum between where we are approximating and where we are centered. All right, so I'm going to change this to a less than or equal to and replace my fourth derivative with that number. I'm about to plug into my calculator, so I'm just going to leave the rest of this. I'm going to make 24 on the bottom to make it easier to plug in. And can you get a number for me? And I want you to see if it is less than that number that they gave in the question. Your calculator may tell this to you in scientific notation. So if you see an E, that is the like times 10 to the whatever. You may know that from science class. I wouldn't even worry about the absolute value. I would just do it, and then if it's negative, just disregard. Yeah. You can if you want. You say how dare you truncate? Team truncate for everyone. All right, did you guys get a number? Did anyone get a number?
Yeah.
Two, what? Team truncate. I heard you. That's why I truncated. Are you team decimal too? Versus team fraction? I'm in a war with one of my AB students about that right now. Yeah, if you wanted to. Yeah. Is this less than 3 times 10 to the negative 4th? Yes, because 2.7 is less than 3. I would want to actually observe this in the question. They're asking me to show that it's less than that, so that should be my final step. If you wanted to be like super notation friendly, I know here they did tell us to use Lagrange error bound. I could like say by Lagrange error bound, especially if that's not mentioned in the question. My computer is lagging. Oh, because the battery's going to die.
Let it die. It's like that song. The Lorax. All right. What? Let it die, let it die, let it shrivel up and die.
Sorry, to me, the Lorax is a book, not a movie. There's a song that's words are let it die, let it die, let it shrivel up and die.
He has a little guy. He has a solo.
All right, I want to do Okay, vote. Break now, break in a minute. Do you want one more question or break now?
Let's just do one more.
One more? Okay. We got to make a Taylor series. So let's look at this guy. We're going to do the one at the top of the next page. Then we're going to take a solid break. So we have f of x equals sine of 5x plus pi over 3. Did you know the one more was going to have trig in it? You're welcome. We want to let p of x be the third degree. So we're going up 2 cubed. Taylor polynomial about x equals 0. So we want to center at 0. You may say, oh, cool. Well, can I build off the sine of x Maclaurin polynomial that I have memorized? No, because that 5x plus pi over 3, if I plug that in where x is, it's going to screw with the center. So we have to do this the good old-fashioned way by taking derivatives of sine. Anything else you want to tell me about these derivatives? Chain rule. Perfect. So my first derivative, what's it going to look like? Cosine of this times what? I'm going to put the 5 out front. My second derivative, negative sine. Perfect. Nate is getting the 25 from the 5 that was there by the second chain ruled 5. 25. Can I stop yet?
No.
Oh, one more? Okay. 125 positive or negative? Okay. All right. Everyone pull out your unit circles. Put them up here. What am I plugging into these?
0.
All right, so if I plug in 0, I'm getting sine of 0 plus pi over 3. So sine of pi over 3. No. We plugged in 0. Do you know the two options at least? 1/2 and square root of 3 over 2. Is anyone? All right. Wow, you guys were much more convincing than my second block. That's this angle. Other people talk to me too. This is the longer version. And this is, does anyone else do trig this way? Longs and shorts? Yeah. Root 3 over 2 is bigger than 1/2, so this guy is root 3 over 2. All right. If I plug in 0 to f prime, I've got 5 times cosine of pi over 3. What's cosine of pi over 3? 1/2, because it's not square root of 3 over 2, so this is going to be 5/2 total. All right, I'm going to stop writing down the work, and I'm just going to write down the answer. What is the next one? Negative 25 sine of pi over 3. Sine of pi over 3 was square root of 3 over 2. Not that bad. All right, last one. What do you think?
Oh.
You're good. All right, and I ran out of room, so I'm going to write my Taylor up here on the top. They said find p of x, not like p sub 3, so I'm just going to call it p of x like they told me to. What's the first term? Square root of 3 over 2. Next term is 5/2. What's the x minus the center part going to look like? Just x. Then minus 25 root 3 over, why is it not just over 2? 2 times 2 factorial. I'm personally going to make that 4 because I feel like it. X squared. Minus 125 over what? 2 times 3 factorial. I'm personally going to write 12 x cubed. And I'm done, right? I don't have to do plus dot 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 here because we're looking for a third degree Taylor polynomial, not a Taylor series. What? What? Because they said find P of X, so I'm just reflecting their notation. All right, let's Lagrange this guy. Lagrange. Yeah, that's all for the first one. So after we Lagrange. All right, so they asked me to find this. And they asked me to show that this is less than 1 over 1200. Cool. So first thing I'm going to do is just plug everything in that is not that z. So I'm going to have f, because this function is actually named f. What number is going to be for my derivative?
4.
I promise it's not always 4. Yes. Yes. Excellent summary. All right, keeping the z, because I got my equal sign still. We want x minus c. What is x? 1 over 15. Notice that's what they're plugging in to approximate. We can see that in their notation there. What is c? Minus 0. What power? What factorial?
Wait, why?
All of those are n plus 1. The degree was 3, so 3 plus 1 is 4. The z is the perfect place where this actually equals this. For us, it's really going to be notational. That's kind of a holding pattern until we find our maximum value. All right, so for this one, I don't have a table. No. So we're never going to know what z is. It's just going to hang out there. All right, so I need to talk about the fourth derivative. Since I don't have a table or anything of it, let's just find what the fourth derivative is real quick. We were pretty good at these derivatives before. What would this fourth derivative be? Would it be positive or negative? All right. So it'd be sine. It would be sine, right? Positive sine. 5x plus pi over 3. What number would go out front? 5 times 125. Anyone know what that is off the top? 625? That sounds right. All right. Now, I am convinced that I can tell you a number that is always bigger than this function. Let's focus on this part of this function. What does sine of x look like if I graph it? You do it with your arm. This guy? I want to know, where's this, the top part? How high does that graph go? 1, right? Sine never goes higher than 1. So I would argue that this graph never goes higher than 625 times 1, right? Because this is less than or equal to. So I would argue that what we could use as our maximum is 625. Now, what I could use, a better version of that, I could look at sine of x between 0 and 1/15th, and I could use, let's see, sine between 0 and 1/15th is increasing, so I could use the value at 1/15th. That sounds harder, though. I want something easy. I know that sine is less than 1, so 625 times 1, let's roll with it. So I'm going to replace this with 625, and I'm going to send you to your calculators. Or do you want me to be our calculator? I actually don't have the number. All right. If we put in our calculator, we would get this number. This is one of three class periods where I like actually need to have my notes next to me. Yeah. What?
So you change like the sign, plus pi over 3 to 1.
So that I know sine, whatever the inside is, sine always has a maximum value of 1. So we're going to use that regardless of the interval we're looking at. We can use that as a maximum value for our sine because it's easy to find and it's definitely bigger. Correct. All right. Why do I care about 1 over 1,944? It's less than 1,200. So we are good to go. Again, you could use by Lagrange error bound if you want. All right, so when we come back from our break, we're going to try to do, I think, just like 2 questions. No, more than that, but it's going to go relative. Oh, yeah, 2 full questions. We're going to skip kind of this question down here to do the 2 on the back page because they're a little bit more fun. But we're going to compare to alternating series error bound again, because if you remember from the Unit 8 test, alternating series error bound was easier than this, yes? So we're going to talk about when we can use that. And then we will finish up one more. Take 4. Yeah.
I'll tell you at the end. I don't really feel like talking.
Okay.
Like I feel like
I don't
talking to
feel
you right
like
now, but
talking
like I
to you
don't
right
really
now.
tell you about it.
It's fine. No worries.
It looked ridiculous.
I thought it was supposed to rain.
It's supposed to. It was a little bit during lunch, and then it like comes off. Yeah, it's supposed to like pour from like 5. It's been humid like all around the school. It's so good.
I wonder if it has flipped over to the air conditioning.
I have no clue what's in most.
Don't you guys love going to the oldest classes? I feel like this thing should be doing something.
Yeah.
Put it on turbo. Oh, that's actually fast.
So, I'm not sure if you're aware, but
Here, let's talk somewhere that's not right next to this thing that's being recorded.
right.
Oh, yeah. Yeah. Just shoot it to me and I can. Yeah, that works. And then, if you want pros and
You're so
I said you sleep right. She'll put the good word. Says you better wash the girls' stalls. Oh, I saw it yesterday.
Like vandalism?
It doesn't even say flush. It says wash. Have you seen that?
All right, let's finish up these notes. So I would argue there's an easier way to do error bound. We mentioned it earlier today. Why do you think I have 3 blanks? If the terms are alternating,
and negative.
decreasing in magnitude. Who was saying yesterday? Who sits there? They were calling it dim yesterday for decreasing in magnitude. That's not a thing. Don't do that. Oh, it's James because he sits in that desk. Oh. And have a limit of 0. If those 3 things are true, then we don't necessarily have to do Lagrange to get our error bound. We can do it by just looking at the next term up. So this question is kind of boring. I want to do the next one because, to use a word that you guys got really mad at the first time I did, I think this one's cute. So specifically the way they tell you about the derivative, I think is real cute. So we got a Taylor series about x equals 2. Hey, there's my center. For a certain function, it converges for all x in the interval of convergence. Cool. That makes sense. That's what an interval of convergence is. And here's the fun part. We've got our nth derivative is given by this formula. So for example, if I wanted to find like the 4th derivative, I would plug in 4 in both of those places. Now that doesn't really work for like our original function. We can't really call that the 0th derivative. That's not a thing. So they explicitly give me the point there. All right, I want you to take about the next. Actually, no, I lied. Let's go. My brain hurts today. All right, so I know what f of 2 is because they told me. I would like to find f prime of 2. So looking at this formula, what am I plugging in for n for f prime of 2? 1. So -1 to the first is -1. 3 to the first, 3. Wow. I want to now find f double prime of 2. What should I plug in? No.
I can feel the wind when I put my hand up.
Who's in charge of the building? All right. What number should I plug in for n? 2. So I'm gonna plug in 2. -1 squared is 1. 3 squared is 9. Because it's the first derivative. Derivative number 1. My first year of teaching, I had a student in my class that was named Juan, so every answer that was 1 was then Juan instead. Juan did not enjoy it. Also, when asked how old Juan thought I was when I was 22 years old, answered 40.
Oh my God.
All right, I want to write a Taylor polynomial, 2nd degree. So what is my first term? 1/3. What is the next term? Some of you know how to write Taylor polynomials. What's the next term? Yeah, over 2 factorial. I'm going to go with 1/18. All right, well, we can write 9 times 2 factorial, whatever. If you want to leave them unsimplified like this, that's cool. X minus 2 squared. Now, did I find enough derivatives? Am I done? Whoa, yay, 2nd degree. So we are going to show that the 2nd degree Taylor polynomial for f about x equals 2 approximates f of 3 with an error of less than 0.01. That looks like a lot of the same words, but one word is very much missing from that statement in that problem. Does anyone notice a big word that's missing? Yeah. Did anyone see the word Lagrange? No. So that's a key to your brain that says, hey, maybe you don't have to do all that. So let's look at what f of 3 actually is. For f of 3, if I plug in, the first one's going to be 1/3. And then conveniently, 3 minus 2 is just 1. So then I'd get -1/3 plus that 18th that we were talking about. Now, that appears to do what I need it to do. Based on that derivative formula, do you think the next term would be negative? Do you think this series is alternating? And you think each time it would alternate signs based on how that derivative is constructed?
Yeah.
What part of that derivative is convincing you? Yeah, that negative one to the n. So I'm going to start my sentence that we have written so many times. It begins with the word since are alternating. As James would say, dimming. And do they have a limit of 0? Does it look like they're getting smaller and smaller to the point where they would eventually just go away? One way to say error when you're feeling lazy, error. It's absolute value of error. I just wrote the word. Why not? Is less than or equal to our next term up. So let's think about how we constructed these terms. What would the next thing here have in it? All right, I agree it would be negative. We're going to throw in an absolute value bars, but that's fine. What else will we use to find that next term? All right, 3 to the third. Where is the 3 to the third coming from? Yeah, our third derivative. Now, why is this not the full term? What are we missing? What factorial am I putting down here? 3 factorial. Now, if I look at that, that's, what is that? 1 over, what's 27 times 6? Number talk, what's 27 times 6? 162. All right. Is that less than this? How about we just use fractions? What fraction is 0.01? 1 over 100. All right. If you want to be real cool, by alternating series error bound. I would say technically no, because we already kind of said things. I'm just being ideal. All right, so if you can find that your series is alternating, I would argue the time spent writing that sentence is a little bit nicer than all of the work that I have to put in for Lagrange. All right, I want to finish up today's notes doing one more Lagrange question, but I want you guys to start it for me. We're going to do the Lagrange part together. So what I want you to do is the front end work. You have a bunch of given information and know those commas in the sentence are not prime. So that's not like -1 over 3 prime. That's -1/3 comma. Next number. I would like you to find me the third degree Taylor, and then I want you to use that to approximate f of 2.8. So it's just to be very clear, in the next about 4 minutes, I'm asking you to do part A and part B. You tell me. Write the Taylor polynomial and see. Good context clues. That's a good follow-up question of why can't I use alternating? Oh, hello.
It is basically what we're doing.
Exactly what you're doing.
Oh,
Yeah, let's hope for better temperature control next week. It is muggy and nasty in here. Ma'am. If you wanted to, I usually try my absolute best to reflect the notation that they're using in the problem. So I'm using P of X because they're using P of X. The likelihood that they would be that picky on the AP test is very, very small. All right, are you guys getting a number? Oh, waiting. Sorry. There's a lot to plug in, to be fair. All right. Anyone ready? What?
Well, there's this, but then sometimes she would write it with P. Is that the same thing?
I was writing that part with R all the time. If I wrote with P, I made a mistake.
Oh,
I use this notation some of the time where we do like our actual value minus our approximation.
using the one given?
Yeah.
Oh, okay.
So
then put it
these
as the R.
are all R's on that side. All right. What number did you guys get? Is it slightly north of 3, slightly south of 4? That number?
Yes.
I am concerned with how much wind is coming through that window.
maybe it broke.
No, but like the blinds are moving.
I didn't get that number, but I plugged in that to the calculator.
One thing, if you're plugging in these like they are right now, make sure you use parentheses around your denominator,
Oh, around my whole denominator or just from the factorial?
around the whole denominator, because otherwise you'll be like for this one dividing by 7, but then multiplying by the 3 factorial.
Okay.
You could also use the alpha y equals to make sure that's all in the denominator. Don't worry too much about it right now. All right, let's do this last Lagrange question so we can look at what happens when we have a graph. So help me set this up. Again, kind of like I've been saying, I'm going to try to reflect their notation as much as possible. So I'm going to use this notation to represent the error. This is just saying the actual value f of 2.8 minus my approximate value p of 2.8. We're going to try to show that this is less than 1/8. Interesting number. All right, so we're going to do the equal sign. Tell me what to write. It's been a couple of examples now. What do I do? All right, fourth derivative. Why 4? All right, fair. I do have a graph of the fourth derivative, so I'm hoping that's the one I want to use. Why else fourth derivative? Yeah, n plus 1, third degree, 3 plus 1, 4. All right, what comes next? All right, x minus c. I like the use of 2.8 for where I was approximating. Minus 2, my center. Power? Factorial. All right. Going to switch to my less than or equal to replace my derivative with something that's easy to find and definitely bigger. I like that Chris noticed we have a picture of this fourth derivative. So let's kind of investigate what's going on right here. Remember, we want something that's definitely bigger, easy to find, but also really we care about the interval between where we're approximating and where we are centered. So this graph, while not very detailed at all, does tell me about things between where my center is to and where I'm approximating. 2.8 is like right here, but we can see it. What number is definitely bigger and easy to find? Let's go with the y value since this is a graph of the fourth derivative. 7. Now, some people might say, well, why don't we use like 6.9 or something? I don't have a scale on this graph. I also don't want to think that hard. 7 is definitely bigger and easy to find. Are the lights flickering? Yeah. Cool. Let's get this done. So I'm going to put 7 in here. 0.8 to the fourth over 24. I'm going to get it done. All right. Let me be our calculator. Anyone know what decimal 1/8 is off the top of their head? 0.125. So we'll 0.119. Is that good? Yes. That is less than 1/8.
So we always make sure that it's.
Yes. And you'll want to state that it's less than. A couple of things. Why, looking at my Taylor polynomial, why was I not allowed to use alternating series error bound? It didn't alternate. All right. So I couldn't use that shortcut because that did not alternate in signs. So if our graph is increasing like this one, we don't really care whether it's closer one way or the other. We just want to make sure that, like, if this is an increasing function, I want to use the bigger side. So if this was a decreasing function, I would use it at x equals 2. Other things. Did this part C tell me to use Lagrange? No. So what I should really do is say that I did. So I'm going to add a by Lagrange error bound. Usually they will be explicit. If they don't, it's nice to remind them of what you're using. And that, my friends, is the end of Taylor series. Nina. So yeah. So the Z is a little bit weird. It's a little bit theoretical. So the problem with the Z is that this thing right here, we're actually going to never find. So the Z is what makes this equal sign true. There is, if we could do this, if there was a situation where I could find a perfect value for that derivative, there is a spot where if I plug it into the derivative, the error is actually equal to that expression. Now that is super difficult to find. It's way beyond the scope of this class. So we're replacing it with something we know is definitely bigger than if I plug that perfect value into the derivative. So really for us, it's kind of a notational step that allows us to do, hey, let's substitute everything else, and then let's do our maximum. Exactly. Cool. All right, what I would like us to do in the last couple of minutes of class is I want to talk about the one Lagrange problem that's on your problem set. One of them's alternating, one's Lagrange. I might bring a couple other ones to look at the beginning of next class just to get some practice. If you want to talk it out with me, we're looking at number 13. This was a little different than the notes, so I just want to talk it through real quick. Yeah. So this one says use Lagrange, cool, to find an upper bound for the error of this approximation. Now, what kind, this is going to be very vague. Do you agree with me that that looks kind of like the Maclaurin-Taylor polynomial or the Maclaurin polynomial for E? If that's the Maclaurin polynomial for E, what would the center be? Where does it look like you're approximating here? What number does it look like you plugged in for X? It looks like you plugged in 1, right? What would our degree be of this guy? 5. All right. So if I'm thinking of the n plus 1s, what do you guys think of those n plus 1s? What are we going to be looking at? We're going to be looking at 6. Now, this doesn't give you a table. It doesn't give you a graph. It doesn't give you much of anything. So if you're looking for what this maximum value would be, I would argue it might be helpful to create your own graph on the interval between where you're centered and where you're approximating. You may know what the graph of e to the x looks like, and whatever side would give you a bigger value, that's the x value I would plug in. If that makes absolutely no sense, try to work on it right now. So try to set up your Lagrange. I would love to walk around with stickers, and I would love to hand out as many as I can by the end of today. We have about 6 minutes left. I would make it your goal to try to get this one question done. What? The center and where you're pressing the one. So it's easier.
Okay. It's happy I just came up.
Cool. I was wondering, what's the date tomorrow? Yeah. Yeah. I'm here with stickers all the time.
So do you just want to?
So I would set everything up first.
Set up like
You're actually prepared with all the stuff we just talked about, where you're supposed to fix that, and then I'm gonna wrap, change from that derivative to that way.
well, what I put
You could write R6 if you wanted, or you could write, like, here's my reason that, or you could just set it up.
He both.
is it?
If Peter
What did
Griffin.
you start doing?
I mean, I already did. I just wanted to go into his bags.
I thought 61.
Is that right?
You have 5 minutes.
Is that right?
So now, you need to think. That function that you're working with is e to the x, right?
Yeah.
So what's the 6th derivative of e to the x? What function is it? Yeah, so maybe graph e to the x and look at it.
Oh, God. Zero. Just like that. Yeah.
I mean, you would want 1 there. Yeah, that's just showing you like look at the first power. So e to the x is your function. Yeah. All right.
So takes that back.
Here with the other square. If you look at it, there's 0.
Take everything out. We're down.
Which x value, if I plugged in, would you think would give me 8?
Bigger spring break will bring Kelly in it.
X equals 0, X equals 1, something.
And then
I
the
think
other's
so,
gonna do
because
it.
these are the things, right? The farther along you go. So for that maximum thing, I would plug 1 into the function. There's a lot of times, I don't like this, and I put there, I like that as interesting. Why did you not? Yeah, so I like all of that. That's what it is.
Because I was just using these as like a term.
So you're gonna want your 6th derivative, the function you're working with is a x equals 1. So think of your 6th derivative.
One
Yes.
6
Over 6 factorial. What's that equal?
I don't know.
So I would grab the x and try to figure out between 0 and 1 what's the biggest.
And then, but then you have to set it. You have to do it close in the. No, I wonder.
So our goal eventually becomes all of that.
Oh, dude, that project is literally like tearing people apart. Dude, and like, she won't let me go. And it's like I know she's fine, but like I feel bad because I don't want to help her. Like, you could keep drawing, and it's like, okay, but I feel like I should like,
5 more.
Yeah, you could. All right, we have 1 minute left. Tell me, do we have a test next class? No. Bring your problem set. I'm going to try to make class as short as possible. We're going to go back to relatively easy math, taking like derivatives of like things like 2x plus 5. And a long time ago. Then when is our test? Wednesday. Round 2 Friday. When is the absolute latest I need your problem set? On Friday. I don't like that one. I would think why not even instead of everybody.
Right before I took it.
Yeah.
I was like,
Maybe one back 100 there.
that's why I like that whole time that we were like doing stuff.
I mean, there's only a 1 out of 3 chance to get one. What did your real class under?
78.
So I'm not gonna be here next Friday because I'm gonna go swimming. But do you think there's any way that I can try to do round 2 like,
Absolutely.
Thursday morning?
Yep. If you want, just remind me the day of the test so I highlight it right away.
Okay.
But absolutely, I think that's a great idea to get it
I'm
done
also,
before a
like,
break.
Leaving early on Thursday
Yeah.
afternoon. So
Yeah,
it's
just
like,
let me know what works best for you, and I will try to make something work because I agree I would want to get it done before break. Thank you. See you guys.
The mock exam with calculators be provided.
Yeah. And I'm going to make sure I made us think about it so calculators will even be provided for the real AP.
They will? Okay.
Because the College Board says we have to. And so I made them stop telling me no because it's in the paper that Dr. Love just signed.
Physics as well, or is it just calculus?
Theoretically, it should be. I am not in charge of the physics exam, and I know Mr. Brown was going to help me get like the calculators down for AP Calc. So it might be worth checking in with Mr. Kim and or he's the one who teaches AP, right?
Yeah.
And or Mr. Weinstein is the department chair for science. Might be worth checking in with one of them.
Can I, if I have the same calculator as those, can I just, if I don't have a charger, can I just like,
Oh yeah, absolutely. Thank you. You too. That is not what I wanted. I didn't hear you coming right
This is how we will.
he doesn't look at the board in the first place.
I'll change your voice to make you.
I don't know.
It was actually easy. This is just no problems that